Hello, it is Laura Hart from Robofun. I am here with my dear friend and colleague, Dr. Stephen Edwards, computer scientist from who now teaches at Columbia University. How are you?
Oh, I'm enjoying the summer. It finally suddenly switched from winter to summer. I remember there was like a couple of days of spring there. I
Yeah,
should have
it's
marked them
true. It
down.
really switched.
Yeah,
But it keeps going, at least for those of us in New York City, it keeps going back and forth. I mean, yesterday was freezing, the day before was hot. You got to really watch the weather.
oh yeah, yeah, absolutely.
So, for those of you joining us, RoboFun is a creative space to learn about technology, coding, somewhat the marriage of creativity and technology. And we run programs all year long. We're finishing our in school programs right now. This Sunday, actually, in one of the ways that I met you, Stephen, we have an open house for our summer programs. So I think of it as a mini STEAM fair from 11 to 2 o'clock at our office at 102nd and Broadway. If you're interested, come by. Bring your kids. If you are interested in our summer camp, which begins the following Monday, the 13th, for 12 solid weeks of camp, come check it out. And you may just show up for the open house or go to the link on our website for Eventbrite. Um, and excuse my cat yowling in the background. So RoboFund's 24 and a half years old, and we work in schools throughout New York City. We work at our studio at 102nd and Broadway. We've just received a National Science Foundation grant with Teachers College, which I'll tell you more about, Stephen, at another point, and we'll be issuing a press release shortly. And in the meantime, my heart to hearts continue every single Thursday, or 90% of them. And Dr. Edwards and I absolutely love talking and have a tremendous synergy. And Dr. Edwards has so much cool stuff to share. So I love bringing him back every 2 months or so. And today we're going to talk about how to motivate kids to want to code. And I thought what would be interesting is the level I'm talking about with my little ones from 3 to 13 is really kind of different than what happens at the college level. And yet, I believe at Columbia, computer science is a pretty popular major. Is that true?
Yeah, it's grown enormously in popularity. We are bursting at the seams, which is a good problem to have, but it's still sort of a problem. And we're not alone. Nationwide, worldwide, computer science enrollments have just gone through the roof. It's crazy. It's a little overwhelming because we sort of barely have the capacity to teach all the students who want to do this. The other amazing thing is I looked recently, and we're teaching between a third and a half of all incoming Columbia students come and take some of our computer science courses. So we're sort of right up there with taking English or calculus or something like that. It's unbelievable the enthusiasm we have for it.
That's fantastic.
Yeah, it's great. Oh, I'll brag about one other thing.
Yeah,
Um,
go ahead.
our let's see, I believe it's our undergraduate class is about half female. So
Yes.
we've managed to balance it out. And everybody asks, "Oh, how do we do it?" And the answer is a whole bunch of things and so forth. But part of it is just that it ends up being a little bit self-sustaining at some point. At some point, you've got enough where you can hire enough really competent female TAs who turn into good role models for them and so
Yep.
forth. And it's just a wonderful thing all around. So yeah, we're phenomenally pleased that this is one of the things that we've managed to accomplish as well.
So does that include computer science students from Barnard also?
Yeah, absolutely. So that's another thing, and I still don't quite know what happened. I've been at Columbia now for over 20 years. When I first arrived, we had 2, maybe 3 Barnard students a semester. Now we've
Uh-huh.
got like 50.
Wow.
And so what happened in the last 5 or 10 years to increase that number? I'm not exactly sure how, but I love it. Keep sending them. They're great. They're just like engineering students, except they speak in complete sentences. It's really strange. But No, it's great fun. So yeah, no, we're getting them in really large numbers, and in
Fantastic.
appropriate numbers as well.
Fantastic.
Hmm.
So, when you think about motivating your students, is that an issue? Like to hang on? Because I mean, one of the things in our email chats back and forth is the precision needed to be a good coder.
Right,
I'd
absolutely.
love to have you talk at some point a little bit about coding, using coding versus saying programming.
Ah, okay. Yes, yeah. Um, so let's see. So the cynical part of me says, "Oh, it's really easy to motivate students. All you have to do is say, this is going to affect your grade, or it's going to be on the test, or something like that." Now, that's not something that you want to do with third graders, particularly, and it's completely inappropriate. And it's a pretty annoying stick to have to use, or carrot, or something like that. And the students end up arguing, and this is easily the least pleasant aspect of my job. But the other thing I realized is that the interesting students are never the ones who just do what they're told, right? And especially if it's really specific little exercises or whatever that they do or whatever. That's kind of not what you want. Um, the thing that you want to engender, and this is the hardest thing of all, is passion, enthusiasm. This is, how do you do this, right? How do you make somebody love something? And you almost don't. I almost think this is sort of the innate part of people's enthusiasms. Uh, uh, I'm not a strong believer in innate skill or anything like that, but I do think there's sort of innate, oh yeah, that's really nice, I really like that, and so forth. And so I suspect we end up doing more or less the same thing, in that we give
We
them.
meaning me with 10-year-olds, you with 20-year-olds?
Yeah, yeah, exactly.
Okay.
That we try to give them exercises that match up with their abilities so that they're reasonably likely to succeed,
Yep.
but also will let them succeed and show them something, something neat, something cool, something that, oh, this is great, I'd really like doing this, how can you do more of it? Um, so for example, in the embedded systems class that I teach, a lot of them implement 80s era video games. And part of that is I know that stuff like the back of my hand. I grew up with it. Uh, it's kind of scary how many neurons I have devoted to Pac-Man and Space Invaders and things like that, because I grew up with all of that stuff. But it's fun because at the end of the very difficult process of creating one of these things in the environment that we have, you've got something visceral that you can understand and you can enjoy and you can show off to other people if that's the thing that gets you get a kick out of, so forth and so on. And so it's this kind of thing. It's how do you want to make sure to give them things so that when they have success, it's, oh yeah, this is marvelous, we got to keep doing it. And
So I missed the beginning of what you said. You said implement A to Z video
oh,
games.
I'm sorry, 1980s era video games.
80s area. Okay. All right.
So think Pac-Man
Yep.
and
Yep.
things
So
like that.
you're having your kids make things like that.
Right. And so they are, what ends up happening, sorry, my collection of notebooks just collapsed here.
Okay.
You can't imagine that happening in my office here. They have to do coding for the game logic, make sure that
Yep.
Pac-Man goes left when you point left, and so forth and so on. But I also have them do the hardware design that actually generates the video, and that's the tricky bit. And I've done that many times myself. It's a lot of fun. It's also very interesting in that when you do something wrong, you can literally see the mistake. So you're generating an image, and this gets back to programming in Scratch and things like that, where you really clearly see what things are doing on the screen, and oh wait, I wanted it to go that way, but it goes that way. That's a pretty immediate way to figure out what's going wrong.
I think what's interesting is that I don't do as much hands-on teaching, although this semester I have been. And the concept of mistake is really more of an adult concept than a concept of for children in the same way. It's like, oh, it didn't do what I meant it to do is such a different thing than I made a mistake. In terms of the stigma and the sort of shame, and it's not about that. It's like, I didn't get the computer to do what I wanted. Okay, what do I have to try next?
Well, that's very good, and I suspect also that may have to do with the environment in which you're having them solve problems, right? So
Right.
Scratch and things like that are very forgiving, right? Unfortunately, in the world that we work in,
Right.
a mistake, if you're lucky, you get an inscrutable error message saying, "Oh, you did this wrong. You're
Right.
putting a square peg in a round hole. Fix it."
Right.
Far more likely is it happily goes through the whole thing and does literally nothing, or stops, or just
Yep.
freezes, or
Yep.
something equally inscrutable.
Yep.
So this is actually a really interesting point, though. It's sort of, how hard of a landing do you have when you deviate from exactly what you're going after?
Right. And also, I mean, I think from the point of view of both of us being teachers, what's the response of the person supporting you at that moment?
Mm-hmm.
And to me, that's a big part of motivating kids is how you respond. There's the positive responses like, well, that's interesting. What do you think happened? And getting the student
Right.
versus, uh-oh, you screwed up. Now that's not a particularly motivating response.
Absolutely. So this may be one of the bigger differences, right? By the time I get them at age 20 or whatever, they're pretty jaded. They've made countless mistakes in their lives and sort of learned to deal with them. The issue there is not, can I engender the right emotional response? They largely have that under control by the time I get them. The issue more is from there trying to get them to think, okay, I wanted to do this, it did that instead. Oh, I didn't expect that. What's wrong with the model of what it should be doing that I should go back and fix?
Right.
And this is the challenge. And what I would imagine you're doing with third grade, 7-year-olds or whatever it is much more about, no, let's persist. This is okay. It's frustrating, but you don't turn that up into, this is too hard, I give up, I'm never going to do this again. You
Right.
want to, okay, cripe, what am I going to do next?
Right.
To try to fix that. And that's
which brings in the big word of grit, which is so big these days. A desire to keep enduring, to keep going. But it has to be interesting enough for people to want to keep going.
Yeah. Well, and to me, that's sort of the central challenge. It's how do you make it so that when the things don't quite go right, how do you go back and correct it? And how do you keep enthusiastic about it? Now, it's almost funny with me. My personal problem is that with these kind of electrical programming things or whatever, I can always think of what to try next. And I will do this, and pretty soon it's 1 a.m. and oh yeah, I should really go back and see my family. They're probably wondering where I am and all the rest of it. And so at some
They
point,
probably know Stephen by this point.
they've figured it out, but it doesn't make it any less annoying somehow.
Right. Yeah.
But this generally isn't the problem with the students. The other challenge, of course, is so being stubborn, that's necessary, but there's also the issue of, how do you take a step back and say, oh, wait, why is this not working? And is there a more clever way to do this? Go ahead.
I think there's an interesting point here, somewhat about, I mean, sometimes in life, this is a good way to approach problems, but sometimes it's not, which is, I remember many times explaining to kids, you don't want to just change everything. You got to change one thing at a time in what you're doing. Because if you change everything, you won't know what got better and what got worse. And that,
Oh,
to me, that's the second point we wanted to get to is how does all this precision with coding relate to the rest of life? And to me, that's a big one.
hmm,
Just like, let's say you're buying a new set of shoes and there's one issue that you have with them and you try changing the laces, but then you change the socks, and then no, you got to just change one thing at a time.
right,
So
right. So this is really, conducting a scientific experiment in many respects, right? This is exactly, okay, if I change just this variable, okay, I know I've got this seems to affect it, and so forth. And absolutely, right, if you change everything, it's kind of like, well, something worked, but we don't know really what it is, and so forth. Um, at the same time, so with my students, I don't particularly have the rip it all apart, try it again from scratch problem. They tend not to do that so much. Um, what they do instead, and I wish we could play video clips here, but I won't. Go look it up. It's Is This It, from the movie UHF, which came out, I don't know, 1982, 1983 or something like that. And it's just a throwaway little gag in this movie with Weird Al Yankovic. And the way it works, and I don't have a Rubik's Cube to demonstrate, but there's a blind guy who has a Rubik's Cube in front of him. And then there's a sighted guy sitting next to him. And what the blind guy does is randomly turn the Rubik's Cube, hand it over to the sighted guy. The sighted guy looks at it, says no, hands it back to the blind guy, randomly rotates it again ad infinitum. This is actually what I see with my students doing, where they do random perturbations.
right.
And that's great, but we've got this gray matter up here that should help us guide to, oh well,
Right.
don't just say yes or no. Say, oh well, this kind of worked, and this is a little bit more of what we want, and a little bit less. So, a little bit different.
So just to tie up this section of what we're talking about, I think we both hit upon it has to be interesting and motivating, and
Right.
you have to want to get to the end goal.
Right.
And the support you get along the way has to be connected to the kind of person, the age of the person.
Right. Right.
Work.
And to play to that person's level of enthusiasm and what fires them up.
Yes.
Right. My wife and I are dramatically different. I really don't care what other people think. I'm an extreme case of this. My wife is just the opposite. If a tree falls in the forest and she can't post it on social media, this tree is still standing, right? It sort of doesn't. And so if you are the kind of person who craves other people's, enthusiasm, and you better put that around them somehow. If you don't care about that stuff, you need something else. What is that something else?
Right.
Which
is, I think that is such a great point. Like, you got to know your students well enough to know how to support them.
Yeah. And that's especially challenging for me because I got into engineering specifically so I wouldn't have to deal with people, and suddenly I have a bunch of them to deal with. It's really annoying. And of course, it's difficult for me to sort of think out of, well, how would I have reacted? I could kind of barely get that. On the other hand, by the time they end up in an engineering program at Columbia, they're cut from fairly similar cloth. Whereas I'm sure you get a much more diverse collection of students going through your world.
One of my thoughts lately that I feel as though in the education world and the world in general isn't talked about enough is that a classroom is a little community. And it's much, much more than this sort of vessel of knowledge being the teacher has. That just doesn't apply at all in my mind. And that you have to operate as a community, and you have to know, the way you talk to student A is often very, very different than student B.
Yep.
And
yeah, that's true. And that's tricky. That's not something I'm very good at. Again, they're much more homogeneous in my world.
Right.
But curiously enough, this is one of the things that fell completely apart during COVID, right? Yeah. One of the big things we provide as a higher educational institution is the community. The person sitting next to you, you ask them, oh, you're ready for the final? Oh yeah, I'm really scared of that too. Oh yeah, this was an awful homework, blah blah blah, and so forth. uh, that's really a big deal.
Yep, it is a huge deal, and
Yeah.
as popular as remote is, and I just had a closing on a line of credit for my business this morning, and I just assumed it was online. And suddenly bankers arrived at my office, and I'm like, oh my God, I'm working from home. And, it was a funny moment, like how much has changed.
Quite.
Anyway,
Yep.
like,
Yep.
you want to close? Come on over. So that ended that. Now, you had a really funny thing you wanted to show us. That's not so funny, but really interesting.
Oh yeah. Yeah. I wanted to, I'll hold this up because this is the kind of stuff that I keep in my office. So
As
this,
witnessed by everything behind you.
yeah. And this is a reasonably wide angle lens, but it's capturing only, I don't know, a quarter, something like that. I have a very crowded office. The best story I have is a student approached me and said, "Oh, Professor Edwards, I need a USB cable or something like that. Do you have that?" "Oh, of course I do. Here, come back to my office. I'll get it for you." I come back to my office with him. I walk in, grab the cable, and it took him about 2 minutes before he realized, "Oh, that's your office? I thought that was the storage room."
Yeah.
Yeah. So this, long story of how I got this. Let's see. You can barely see the numbers on the front. This is a decimal counting unit. And so this is from probably late 50s or something like that. And it counts 0 through 9 and then circulates around. And it does so kind of in binary. It's in binary coded decimal. But here are the 4 bits that it uses. Each one of those is a dual triode vacuum tube. And each one of them operates as a flip-flop. So here is 1 bit. Here is the second bit. It doesn't quite count in binary. There's some trick where it's how do you get it so instead of 16, it counts up to 10 and then resets and all the rest of it. But it's just sort of mind-blowing to me that something this large and heavy, and it takes, what is it? So the filament, the thing that heats it up to send the electrons, is like 6.3 volts or something like that. Okay, yeah, that's not too bad. And then the high voltage is like 250, 300 volts or something like that, which is just, unheard of these days, right? It's like, not quite, neon sign voltage levels or something like that. But to me, it's wonderful, and I'm going to wake this thing up at some point and actually show it. There should be lights going up here showing you how it counts and so forth. And it's both incredibly foreign, alien, right? None of these students would have ever seen an operating vacuum tube or would have used one in their lives. I mean, heck, it disappeared when I was a kid, the use of tubes for most things. But at the same time, binary, counting in binary with ones and zeros, same idea. That's been around, since ENIAC times or whatever, 1940s or something like that. Using individual bits and representing them as bits, and then having some individual thing that can either be a 1 or a 0, and it will hold its value and so forth. That hasn't changed either. So to me, the joy of all these historical artifacts, and most of the stuff behind me and around me and so forth is much more historical than anything else. To me, the interesting part is what's the same, what's changed. What from this thing has continued into the modern world versus, oh, that was a horrible idea, let's throw that away, or something like that.
So where did that come from?
So the story with this, so I bought this off of eBay. It came out of
that's an unusual thing for you, I would guess. Versus
I usually don't have to bother with that. I usually just find this stuff being thrown out at Columbia. I learned about this at a vintage computer festival that I attend down in. If you look up VCF East, you can find it. This is down in New Jersey. Somebody brought the piece of test equipment that this was part of, and it had, I don't know, like 6 or 8 of these in a case, plus a boat anchor transformer, plus a bunch of other stuff and so forth. And I saw this. I understood exactly what it was. Wonderful thing. It wasn't going to fit in my backpack to come home on the train with me, and so I wanted instead, okay, let's just buy a piece of it.
Interesting.
and so forth. So yeah, a lot of fun.
All right, I
Uh,
have a
Go ahead.
question for you.
Yeah.
So we've touched a lot on how to teach programming. Oh, okay, well, actually, let's talk about programming coding.
Yeah.
What's your take on the field where programming was the term and suddenly it went to the
Oh,
side? Coding is
so there's two components, and I try to teach my students this as well. There's coming up with the algorithm, the sequence of steps to do something.
Mm-hmm.
And if what you're doing is making some little thing animate on Scratch or whatever, the algorithm is pretty straightforward.
Yep.
If what you're talking about is machine learning or something like that, the algorithm gets very, very complicated. The algorithm is sort of orthogonal to how you express that algorithm to the computer. And once you choose a language, be it Scratch or Python or C or Java or whatever, then there's the issue of how do you take that algorithm and express that and code that in the language that it's looking at. And so, I try to teach the students, hey, work out the algorithm first, code it however you want to make sure you understand the algorithm, but make sure you understand the algorithm. Then let's worry about how we implement that algorithm in the most efficient way, the most appropriate way, or whatever. Usually these two things are very closely intertwined. And if you look at Scratch or something like that, they are, appropriately so. This is not really a concept that 7-year-olds need to be worrying about.
Right.
But by the time they get to be 20 or something like that, you've got a panoply of choices for implementing a particular thing. And for the particular algorithm, how parallel is it? What is the, do you use this kind of representation or that kind of representation? And you've got this abstract bit of it. Do you use this sub-algorithm or that sub-algorithm? It sort of goes on and on. And so there's a bunch of choices, but understanding that there's two big challenges there that you can and often should completely separate. Maybe that's the distinction.
So you think of programming as the overall umbrella and coding is the way that you.
Right.
Yep.
Right.
Okay.
Something like that. I mean, I would imagine there's an equivalent thing in writing English. I don't know what it would be, where it's, coming up with the story idea and the story arc and how all that works together. But then there's the detailed issue of, how do you write the dialogue? How do you write the sentences that communicate this idea?
Mm-hmm.
And for a given story arc, there's many ways to write it, some better than others.
Yeah, that's yeah. So the last issue, and as usual, we're almost out of time. We might start this now, come back to it in a bit.
Sure.
Is why do we teach kids programming?
Why do we teach kids programming? Absolutely.
And young adults, for that matter. So.
Yep, absolutely. So it's interesting. I was just reading a history of computing book, and it made a very interesting point that nothing has changed more rapidly and had more effect on sort of the way people live than computing, right? In a little longer than our lifetimes, it's gone from nothing to everybody has a cell phone, able to access the entire world's knowledge and share cat pictures. And it's not going to stop. And there's nothing like that. And so it's absolutely ubiquitous. To me, the fundamental thing is knowing its abilities and its limitations. Right. I was just having this discussion with a friend of mine about machine learning, which is the big hot topic in computer science for 20-year-olds these days. Everybody wants to do machine learning.
And we will catch that topic on another call.
Absolutely. But, what is it? What is its limitations? What can it do? What can't it do? What can we expect it to do, right? What can we expect it to do? The answer is do not look at Hollywood movies for guidance on these issues, right? These are fanciful, entertaining things that generally don't take physics or logic or anything else into account, which is fine. This is entertaining, but just don't think of that as being representative.
Yep.
And so the huge pile of rogue computer gets control and takes over the world. I'm not really worried about that. I'm much more worried about human beings doing that. What kind of mistakes can they make? What kind of things can go wrong when you train a machine learning system with a bad corpus of references? What can you expect to go wrong? Other really basic things like, you go to a website and this doesn't quite work, right? Oh, how do I log in with this? How do I forget this? How do I remember this password and so forth? These are basic life skills right up there with, balancing checkbooks and holding down a job and so forth. And so to me, that's sort of the practical societal, why we should be teaching everybody this and not just the extreme nerds who are going to love it anyway.
Right. Well, I think there's another side of it, which I suspect you're going to agree, but I like the idea that you have a big problem and you have to take it apart and figure out what is that big problem made up of. And then you have to solve the little pieces of it and put it back together.
Absolutely. And so problem solving in general, and maybe take it one step further, quantitative problem solving in general is an important thing. And the reason I didn't go there immediately is this is also why we teach mathematics to students, right? I had a discussion recently. Why do we teach geometry to 14-year-olds, 13, 15-year-olds or something like that? I don't know. Laura, what's your thought on that?
My thought is that there's this missing piece that we as educators have to get better at, which is A, to make it really interesting, and B, to explain that at the beginning. I don't think we explain that enough to kids, but I loved geometry and algebra. I thought it was really interesting, but I think that, a colleague of mine, Jane Margolis, has written a bunch of books on unlocking the clubhouse, how to get girls more involved, how to get minorities more involved. And I think it's the same kind of thing, is that it has to relate to people's lives. And if it has no relationship to people's lives, it's a problem.
That is the common refrain that I hear. It's useless. I'll never use it and so forth. Well, in fact, you will. You won't realize it, or you won't do it very well, or something like that. Right. Specifically with geometry, with the exception of people who are actively drawing things, or architects and engineers and things like that. Yeah, it's not clear what the practical use of all this stuff with the circles is, but the reason it's taught is to teach mathematical proof, and the notion of starting with axioms and then building theorems on top of that, and what constitutes a phenomenally sound mathematical argument. Now, the other interesting bit about that is that arguments like that, there's a class of them that's used for mathematics, there's another class used for engineering, there's another class you use in law.
Right.
And in fact, it's worth knowing how all of those fit together and so forth. But of course, nobody bothers to tell you any of this when you're learning it in ninth grade or whatever it is,
right.
Because we're too busy. Oh no, you've got to learn that this is what right triangles are, stuff like that.
Right. So I think we miss a piece, and I think also, again, as my son was picking classes in college, I was like, in some ways, what matters is how excited the teacher is about what they're teaching, because that's what makes a good learning experience. Somebody who wants to be teaching what they're teaching.
Oh yeah, no, that's absolutely it, and it's as simple as humans are empaths, right? It's hard to get enthusiastic from a person who just doesn't care.
Right.
On the other hand, as a parent of a teenage girl, I can say that I can be phenomenally enthusiastic, and it does not rub off.
Right.
So,
again,
it can go either way.
It's finding your audience. I think this is a good moment for us to pull things together and say, for one, caring teachers to me is everything. And for my little company, Robofun. We have a training on Saturday and all these incredibly interesting new curriculums. And Sunday we have our open house. So I encourage those of you out there who are like, oh, what am I going to do with my child this summer? We have week-long programs all summer long for 3 to 13-year-olds. So go to robofun.org. If you're enjoying this time where Stephen and I talk and you want to share it, my marketing people are like, you got to put that in. Tell them to share it with friends. So if you're enjoying this, please share it. Let us know. Give us a thumbs up on Facebook. And again, open house on Sunday, summer camp all summer. And Stephen, we're going to pick this up in a couple of months. And again, I'm so grateful for our friendship and to learn about your work and to be able to share it.
Oh, this is great fun. I will also plug the your open house. It's a very quick, easy, cost-free way to go and check out Robofun and see the physical environment and see what kind of things the kids do and the people who will be teaching them and the environment and all the rest of it. You can look at websites, but it's a lot more effective. Just go there, meet the people, see what's going on, see the kids playing enthusiastically with any luck. Makes a lot of sense.
Your issue may be getting them to leave. So not, once
if that is your issue, you have succeeded. Yes. Mm-hmm.
Right. So thank you so much. And thank you for our audience today. And we'll be back in the next few weeks. Thank you.
Very good. Hey, thank you so much.